This is second part, that is second video in the series of electromagnetic induction lecture, in which I plan to do these topics. First, Fleming's right hand rule, methods of generating EMF, motional EMF in rotation, energy conservation, and lastly, relation between amount of charge induced and change in flux. So let's begin with Fleming's right hand rule. A lot of students think while discussing Fleming's right hand rule that what's the difference between Fleming's left hand rule and right hand rule? Fleming's right hand rule is concerned with induced current only. That means whenever electromagnetic induction is to be talked about, then only Fleming's right hand rule is needed. Otherwise, in general situation of magnetic field and magnetic force, always Fleming's left hand rule is needed or discussed. Fleming's left hand rule was FBI, that means force, magnetic field, and current for thumb, index, and middle finger. Same way, this time for Fleming's right hand rule, again, same way, this time right hand rule. We are to think on the line of same pattern, V, B, I, velocity of straight conductor, B, magnetic field, and I is induced current, such that these three physical quantities are mutually perpendicular to each other. Then velocity of straight conductor should be along thumb, B, magnetic field should be along index finger, and third, middle finger, along which induced current should be located. And when out of these three, two directions are given and third is to be found, then only Fleming's right hand rule is to be applied. I must mention it is thumb, index, middle, and you should remember VBI instead of FBI. So this was Fleming's right hand rule. Let's see, whenever we would be needing, we'll apply that. Here comes our second topic, was methods of generating EMF. Now I would be considering a solenoid. Around this solenoid, I'm to consider one circular coil of n turns whose radius is B and radius of this solenoid is A. So let us consider this solenoid having time varying current. Time varying current I is equal to I naught sine omega t. Time varying, that means current is varying with respect to time. Number of turns per unit length n. Number of turns per unit length n, and radius a. Let me indicate again with some other color. Radius a, and this is n number of turns. And already we know magnetic field due to solenoid is mu naught n I. Mu naught n I is replaced by I naught sine omega t, and phi is NBA. In general, flux is B dot A, but considering total number of turns, so phi is NBA. By that, phi is NB mu naught N I naught sine omega t, and A is pi A square. Remember, I'm telling you in advance, wherever mutual induction is considered, that means one here in this diagram, both if this solenoid has a current, time varying current, then because of this green circular coil having n turns will have induced current because of this current. That means it is a case of mutual induction. Later on, I'm going to clarify in third video in detail what is mutual induction, but I didn't plan to discuss mutual induction in the current video. For the time being, you just take mutual induction is the phenomenon in which primary and secondary coil both mutually induce each other. Okay, so here again, and for mutual induction, any and every time smaller radius is considered, whether this induced current or this green coil induced current. In both the induced current, we need to consider smaller radius because empty space between this, that means this is empty space. This has got no magnetic field lines. Hence, this larger radius is irrelevant for mutual induction. That's why we have considered small radius only. Therefore, induced EMF, E is minus d phi by dt. Now, I'm to differentiate this whole expression. And while differentiating, we'll be taking out all the constants out. Only variable are to be differentiated. Minus d dt of n mu naught n I naught then pi a square. And all these constants will be taken out minus n mu naught n I naught pi a square. And here variable coefficient is omega. So that will also come out, and differential of sine is cos. So this much large the expression is. Now second method, theta as a function of time. This is also quite popular. For this, I'll have to show into the plane magnetic fields. Now it is B into the plane. Now circular coil. This is A. A is the radius and omega is the angular velocity about this axis of rotation. Situation you must have understood. Omega is the angular velocity rotating the coil about the axis of rotation. Then phi is NBA cos theta because it is phi is in general B dot A. So here NBA cos theta. And then later on, theta is equal to omega t is to be considered as S is equal to Vt. It implies that phi is NB for A, we'll be considering pi A square. Yeah. And thereafter, differential of cos omega t is minus sine. Therefore, E is minus d phi by dt is equal to minus n b pi a square ddt of cos omega t minus n b pi a square minus omega sine omega t. Minus minus cancel. E is equal to n b pi a square sine omega t. This is what our target was. Now coming back to our original list, third topic we are supposed to do is motional EMF. That means EMF induced in a coil due to motion of something. In fact, that something is straight linear conductor of length L. Next topic is motional EMF, in which we are to study the appearance of induced EMF due to motion of straight conductor. That means here in the current situation, straight conductor will be moved through the velocity v, such that magnetic field B, length L of the rod, and V, velocity of the rod, should be mutually perpendicular. Then only motional EMF will be appearing. Otherwise, there won't be any motional EMF, right? Let's see the situation. Again, I'll explain this thing. This is known as a rail because it is very much similar to railway track. So this is the rod. The rod is at a distance. L is the length. This is V, velocity of straight conductor. The EMF generated by moving a conductor in a magnetic field, that is, by changing the flux in the circuit, is called motional EMF. That means when this rod is moved in this leftward direction with speed v, then magnetic flux is changing. How? Why? Because in the process of movement of the rod, this whole thing is area is decreasing in the process, and hence flux is decreasing. And if flux decreases, that means EMF will be induced across the ends of the rod. These two are the ends, and thereby induced current will be appearing here along the rod, and then thereafter current will be continuous in this closed loop. But the problem arises how to find the direction of induced current. That for that purpose, we'll be applying Fleming's right hand rule. And then let us apply right hand rule. Let's see what our Fleming's right hand rule said. Initially, we had a discussion on this. V, V, B, I, velocity of straight conductor, thumb, magnetic field, index, and induced current, middle. Now, I'll be considering C. This is into the plane of my laptop, into the plane, and this thumb is pointing towards the motion direction of the rod, which is leftward, and direction of induced current rightly across the PQ end. This is induced current. And here V is constant speed. Now, while discussing mathematical analysis of the situation, we'll be considering constant speed. There is no loss of energy due to friction. That means we are considering ideal situation. Then by using Faraday's law, phi b is BLX. Phi b, that means magnetic flux. Magnetic flux is B A. B is already given, and area is length into L into X. Length of the rod into X is the separation between this length towards the end of the rail. Here, X is changing with respect to time, Faraday's. Therefore, E is minus d phi b upon dt minus d dt. BLX already we had, that is equal to, it implies that E is BLV. So this is motional EMF. And point to be noted here, for appearance of this particular type of induced EMF, always B, L, and V should be mutually perpendicular. Otherwise, there would be no motional EMF. Now, same expression we are to analyze and conclude by using Lorentz force. Lorentz force, mainly this would be needed for tackling JEE mains related questions and even advanced level also. Here induced charge is also taken into account. The charge Q in the conductor will also move same velocity as the charge will be moving in uniform magnetic field, then definitely it will be experiencing magnetic force QVB, charge Q of force F equals QVB towards. Now, for this purpose, we are to apply Fleming's left hand rule because now magnetic force is taken into account due to moving charge. So let me apply magnetic field into the plane of my laptop screen and force direction and positive charge is moving and rightly my thumb is pointing downward in air. That means if we consider my laptop screen, then it is P2Q. This is magnetic force. I guess you must notice this magnetic force, and this direction was determined by applying Fleming's left hand rule. Work done in moving a charge from P to W is equal to force into displacement, and force is QVB, but EMF is the work done per unit charge. Therefore, E is W by Q. W is QVB into L upon Q. Therefore, E is BLV. So just now, we proved the expression for motional EMF by second method, alternatively by using Lorentz force. Again, here also we obtain E is equal to BLV only. Now, how to determine the direction of positive polarity of motional EMF? One method was already I told you, that is to apply Fleming's right hand rule, because by applying Fleming's right hand rule, we are able to determine the direction of induced current. So indirectly, we are able to find the polarity also of this induced EMF generated across these two ends. If this is the direction, then obviously positive polarity will be here and negative is here. And alternatively, polarity is direction of positive polarity, direction of V cross B. Now I'll explain how. For example, this is a rod of length L. This is B into the plane. Now I'm to apply V cross B. Simply cross product. I'm applying cross B. So first vector to second vector, anti-clockwise this way, positive polarity, Y, L sine theta, Z, B, direction of EMF, E is BLV, sine theta. Another example, second example, this time rod P, L, X is equal to L, B is, Y is cos 90 degree, Z is B. Here, E is equal to 0. Since any two of B, L, V are parallel. What do we learn then? B, L, V out of these three, any two is parallel, then no motional EMF. So that is the point, right? General formula became for motional EMF. E is V cross V dot L. Now, last point under this heading would be for stationary conductor. In case of stationary conductor, the force on its charges will be already you must be knowing F is equal to Q V cross P plus E, which is already dot E. V is equal to 0 because we are talking about stationary conductor. The force must be due to E. Therefore, to explain the induction of current, we must assume that a time varying magnetic field generates an electric field. And time varying magnetic field generates an electric field. This kind of point we'll come across while studying electromagnetic waves. But the electric field due to static charges and that due to varying magnetic field have different properties. And time varying magnetic field, that means dB upon dt. Hence, we have discussed this point also. And here under this heading, we are to consider some rod of length L has to be rotated in perpendicular uniform magnetic field. In this kind of rotation, flux lines are being cut. So that's why induced EMF will be appearing across these two ends of the rotating rod, such that one end is fixed at the center of this virtual circle and the other end is rotating, forming the circumference of the virtual circle. This thing only we are to, and one standard formula E is equal to half B omega L square R to B is to be used all the time. Just formal proof. We'll be doing so in two ways. That is, two methods we'll be following. Now, discussion is very small, although this is the rod of length R, which is constituting the radius. This is the rod of length R. In the process of rotating like this, radius of this virtual circle is length of the rod R. The charges in the rod experiences of force and move towards O. At a certain value of EMF, there is no more flow of electrons and steady state is reached considering elemental length dx at distance x from O. As the rod moves perpendicular to the field, the magnitude of EMF across dx will be dE is equal to dV dx. Now I am to consider in the same diagram, suppose here dx at a distance x. Omega is the angular velocity with which the rod is being rotated about O. Firstly, I am to consider this dx element. Because of this dx element, we'll have very small induced EMF dE. So I'm intended to write the expression for dE first, then afterwards we'll be integrating that dE and limit would be 0 to capital R. So here it is. whatever thing I explained, this is dE is equal to BV dx on the line of BVL. And since V is equal to R omega, so here V is equal to, in the given picture, small r is capital R and then dx is R. Here dx is the, for a small element, this is the radius. So V is equal to x omega. It implies that dE is B x omega dx. It implies that E is equal to P omega x dx, limit from 0 to capital R. X square upon 2, 0 to R. It implies that E is equal to B omega R square minus 0 square by 2. Therefore, E is equal to half P omega R square, and it is very, very important. An alternative method also I'm willing to use, that is again very, very simple. Alternatively, area swept by the rod. Area swept by the rod in covering theta of angular displacement. This area would be area swept by the rod in covering theta angle at the center, angular velocity omega. A is pi r square into theta by 2 pi. That is equal to theta r square by 2. This is just by using the concept of ratio and proportion. Therefore, phi is BA theta r square by 2. It implies that mod of E is d phi by dt. That is whatever thing we obtained. Now we have to differentiate. It implies that E is, all will come out b r square by 2 and d theta by dt. And that is from the basic fundamental of rotational dynamics. E is b r square by 2. It is omega. Therefore, E is half b omega r square. Hence, it is tan. Omega is d theta by dt, as V is ds by dt.